Hello everyone, I'm Sothea and currently I'm a second year PhD student at Sorbonne University, but I'm working at the laboratory LPSM of Université de Paris. And today it's my great honor to be able to present my first research topic about a cluster-wise supervised learning procedure based on aggregation of distances applied on energy domain. And the motivation of this procedure is because based on many literatures, we know that modeling is a common tool used in many real-world prediction problems, especially in the domain of energy. But to construct a good model with a great generalization capability is not an easy task, and it may require information of unknown data structure that is most of the time not available. That is why we propose this three-step procedure to automatically combine efficiently both idea, clustering, and modeling together. And it's called a KFC procedure because of the step of this procedure. And we observe so many satisfactory performances of this procedure on many simulated and real data sets, especially on the domain of energy, air compressor, and wind turbine. That is why I would like to bring this topic for this summer school today. So I will describe about the three steps of this procedure, and then we will consider some application of this method on energy domain, specifically on air compressor and wind turbine at the end. So to begin, let's consider some toy example. You can see on the left that there are two predictors, X and Y. They are predictors, and together they form up three clusters: red, blue, and green. And on the right, we include also the response variable Z, which we want to predict using X and Y. And clearly, Z is defined differently on different clusters. So this is exactly the idea of what we are doing here. So with the standard setting, let's denote X and Z, the input and output data. X is assumed, the input is assumed to be in RD, and Z is either R in regression problem or 0, 1 in binary classifications. And Dn, which is the training IID data of size n. And the objective is to try to construct a good predictive model for regression or classification adaptively to the previous kind of data set, or more specifically under the following assumption. The first one is that X is composed of more than one groups or cluster. The second one is K, the number of cluster K is available. We suppose that it is available here, but we can see later that it is not so important. And the third one, which is really important, that the underlying model on each cluster is not the same. It's not necessarily the same. They are different from one cluster to one another. And to solve this problem, we propose this, under all this assumption, we propose this three procedure, which is a KFC procedure. It consists of three important steps. The first one is K step, which is K-mean with Bregman divergences. The goal is trying to approximate the clustering structure of the input data using several dissimilarity measures, several options of them. And each of them will lead to a specific partitioning structure of our input data. Then we construct local model, as I shown in the previous slide, that we construct a local model for a given structure, and then the collection of all this local model will be called a candidate model. And because we perform K-mean with several dissimilarity or Bregman divergences, then at the end we will combine all of those candidate model together. And this is the three steps of this procedure, and I would like to describe a little bit about the most important tool for this study is the Bregman divergences. It's defined associated to some strictly convex and continuously differentiable function phi's. And the dissimilarity between the Bregman divergence between X input data X and input data Y is defined as the difference between phi of x, exactly at point x, minus it's the difference between the linear approximation around point y of function phi, but again evaluated at point x. So this difference is exactly the vertical black line here, and it carries many interesting properties such as non-negativity, obviously, and Euclidean distance is also one of them. And what I want to point out, without any technical stuff, I just want to say that, well, different Bregman divergence would behave differently in clustering our input data. That's all what I want to say. And then in the first step, which is the case step, we propose to we use m options of Bregman divergences in to perform k-mean algorithm. And then because each of them behave differently, then each of them will end up having the associated partition cell, which is called SL, and there are k cluster inside this SL. So at the end of this case step, we end up having m partition structure of our input data, and because our data set is somehow looks like this, and then in the second step, suppose that we have enough data point for all the clusters, for all the Bregman divergences, and then on each cluster we construct a local model, which is denoted by mk on cluster k of Bregman divergent L. And this should not be very complicated. It should be just based on our experience. It should be really simple, like linear regression and logistic regression in classification problem. It should be okay. And then the collection of all these local models will be called MLs, which is the candidate estimator associated to Bregman divergent L. And at the end of this step, what we have is M's. We have M's candidate models corresponding to M's Bregman divergent we used in the beginning. And at this step, we should note that neither the distribution of the input data nor the clustering structure is available. We don't know them in our problem, in almost every problem. So it's not easy to choose the best one among them. We don't know which Bregman divergent provide the best clustering structure of our input data. That is why we propose to combine them in the C step, with what we call consensual aggregation method. And this one is really simple, the idea. Let's consider some example. Suppose we have M in classification problem. We have M classifiers, M1 until M4. And the prediction of X is given by the 4 classifiers, 1, 1, 0, and 1. And to predict the real level of X, we just consider the prediction of all the training data. In this case, there are 5 of them. And we look at only those data points with the same predictions as X. So it's 1, 3, and 5. Then we take the real class of this data point and we do the maturity work. This idea was proposed by Mougeot in 1999, and it's a really nice theory about this one. And also later he proposed a kernel-based exponential kernel-based method of this one, just to take into account also those data points that the prediction is not completely agree with the prediction of X, but somehow agree at some level. We also take into account them. And then the last one, which is the method taking into account also the input part. We do not compare only the prediction part, but also the input part, which is called mixed cobra, introduced by the 2 of my supervisor, Aurélie Fischer and Mathilde Mougeot. So this is what we used to combine in classification problem, but we would like to focus more in regression problem in this talk. So the combination is defined as a linear combination of the response variable Z, and the weight is defined differently. For example, in the first one, is by Mougeot et al. In 2016. It is called Cobra method, classical Cobra method, where the weight is defined almost similar to the previous case of the first case of Mougeot. We do not say that the prediction of all the trained data is exactly the prediction of X, but we say that they are close enough. To say that they are close enough, it means that each component of the prediction is close to each other at level epsilon or some epsilon. And if it satisfies this condition, we will give this training data xi some uniform weight, which defined in this formula. And the goal is to learn a good parameter epsilon, minimizing some cross-validation errors. And later, I propose in the second step, this is my work, and I finish it. It's a generalization of this case to more regular kernel, to more general kernel. And the last one is again mixed cobra that take into account also the input part. And this is what these are the method that we use to combine all those candidate estimator ML at the end of our procedure. Then in the application, in this simulation, in this talk, we will use these 5 Bregman divergences, which include including Euclidean descent, general Kullback, blah, blah, which are very well known. And I just want to show a little bit about how this Bregman divergence behave in clustering our input data. For example, in this image, it's exponentially distributed. And there are 3 clusters, vertically, horizontally, and in the middle. And you can see with Euclidean distance, it's normal K-mean. And with other distances, other Bregman divergences, the one that recover the closest to the reality is this one, Pythagoras cycle. Because there are relationship between the two. The two, they are linked in some theoretical perspective, but I don't want to mention that. I just want to say that they behave differently in clustering input data. And for the first example, for the first application, is air compression machine. And it consists of 6 predictors: air temperature, input pressure, output pressure, flow, and water temperature. And the goal is to predict the power consumption of this machine. But in many real-life problems, we don't know K. We don't know how many clusters are there in this data set. And it's the case here. So we perform our procedure of using several options of K. And in this, table contains average root mean square error of 20 repetitions, randomly splitting our data set, 80% training and 20% testing. And the value in the brackets are the associated standard error. And as you can see that when we increase the number of K, in this first block with 4 columns, they are ML, they are candidate estimator. We construct up to F step. So this is with Euclidean descent, this is with GKL, logistic, and Pythagoras cycle, and they perform better and better when the number of clusters increase. Well, naturally, it should be like this. And then in this last 2 columns, we combine these 4 using Cobra method with Gaussian kernel, which is my method in the second point. And we can see that, well, it's good. It's improved the previous performance of our 4 candidate estimator. But surprisingly, with mixed Cobra, it improves very, very much. And more importantly is that it does not depend very much on the number of clusters. Even we combine the bad team, these 4 guys, which appear to be bad comparing to this. But it's still, we obtain something that is really good. So this is the strong point of our method, that maybe we don't know the exact value of K, but it still works. And we compare also the performance of other models like multiple linear regression, this level, and KNN, 22K, random forest and boosting with 500 trees, and we still perform better than this method. So it's just to say that even we don't know K, KFC procedure still does the job really well on this data. And the next one is win-to-win data set. And it consists of 6 predictors also. The characteristic of winds and the temperature. And the goal is to predict the power produced by this turbine. And again, we don't know K, so we do the same thing with several value of Ks. But in this case, we use only 2 options of Bregman divergences because other Bregman divergences not works. They don't work on this particular data set. So we use Euclidean and polynomial Bregman divergence, and we can see the same thing, that they behave better and better when the number of clusters increase. But when we combine them, we obtain something really nice. Even just 2 of them, then we could, when we combine them, we obtain something really great. And it does not depend very much on the number of clusters, just like before. And mixed comprise the one is the hero in this case. And we compare also 2 alternative models, and we still do better than them. And it's the same thing that even without the exact value of k, we still could perform well using our procedure. So at the end of this, in conclusion, we just want to say that depending on many simulations, on the simulated data and also real data set other than energy data, we observe something, we obtain something that is really remarkable with this procedure. And we hope that it should be a good way to solve some problem involving clustering and modeling. And in particular, with this energy domain, we really obtain something really great, as I shown in this talk, especially on these 2 data set, air compression and wind turbine. And that's it. Thank you very much. These are some references for this talk. And thank you for your attention, and goodbye.